Welcome to another deep dive.
Oh, yeah.
Today we're tackling gravity,
Oh, fun.
but not just the apple falling from a tree. We're going deeper, exploring the relationship between gravitational field strength and gravitational potential.
Okay.
Get ready, because there's a real aha moment waiting for you when we unlock how calculus connects these two seemingly separate ideas.
Awesome.
Our guide for this journey is a fantastic educational website, full of clear explanations and interactive simulations.
Cool.
It's going to be like having a physics tutor right there with you.
What's fascinating about this topic is that these two concepts, gravitational field strength and potential, are often taught separately. But in reality, they're deeply intertwined.
Okay, so before we get to the calculus magic, let's start with the basics. What exactly do we mean by gravitational field strength?
Think of it this way. Imagine you're holding a ball. You feel its weight because of Earth's gravitational pull. That pull, that force per unit mass, is what we call gravitational field strength. It's represented by the letter G.
So G tells us how strongly a mass feels gravity's pull at a certain point.
Exactly. And importantly, G is a vector.
Now, I remember vectors from high school physics. Those are the things that have both size and direction, right?
That's right, like an arrow pointing in a specific direction. So G not only tells us how strong the pull is, but also the direction of that pull.
Makes sense. Now, what about gravitational potential? This one always seemed a bit more abstract to me.
Think of it like this. Imagine you're holding that same ball high above the ground. It has potential energy because of its position within Earth's gravitational field. The higher you lift it, the more potential energy it has. Gravitational potential, represented by the Greek letter, is that potential energy per unit mass.
So while G is about the actual force, is more about the stored energy due to position.
You got it. And unlike G, which is a vector, gravitational potential is a scalar. It only has magnitude, meaning it only tells us the amount of potential energy, not the direction.
Okay, I'm starting to see the distinction here. But how are these two concepts linked? And where does calculus come in?
Well, look at the units we use to measure them. G is measured in newtons per kilogram. A unit of force per mass is measured in joules per kilogram, a unit of energy per mass. The units themselves hint at a connection between force and energy. And that's where calculus comes in. It gives us the tool to express this relationship precisely.
All right, I'm intrigued. Can you reveal the equation that connects these two?
The equation is G equals d dot r. Now, I know that might look a bit intimidating with the d's and all, but don't worry, we'll break it down.
Perfect, because I'm definitely feeling a bit intimidated right now. Please break it down for me.
That d dot r part represents the rate of change of potential with respect to distance. Think of it like this. Imagine you're driving a car. Your speed is the rate of change of your distance over time. In this equation, d dot r represents how quickly the potential changes as you move closer to or farther away from the source of gravity, like the Earth.
Okay, that makes sense. So watt r in the equation represents distance.
Yeah, exactly. It's the distance from the center of the source mass, like the Earth. So det tells us how much the potential changes for every little step you take closer to or farther from the Earth.
And what about that negative sign? What's that all about?
That negative sign is crucial. It tells us that as you get closer to the source of gravity, the potential becomes more negative. But the gravitational force you feel, Yi, actually gets stronger.
So it's like a seesaw. One goes up, the other goes down, but they are both connected somehow.
A great way to picture this is to imagine a graph. Put app on the vertical axis and r, the distance, on the horizontal axis. Now, the slope of that graph at any point represents G at that distance, and that negative sign just means the slope goes downward as you move closer to the source of gravity.
Okay, let me see if I've got this straight. As you move closer to Earth, your potential energy decreases, but the gravitational force you feel actually increases.
You nailed it. That's the key insight here. The rate of change in potential energy directly translates to the force you experience within the gravitational field.
This is starting to make sense now. But how does this all apply to real-world situations? Like, why should someone who isn't planning on becoming a physicist care about this?
That's a great question. And you know, this connection between G and isn't just some abstract concept. It has real-world applications, especially in things like space exploration. Think about planning a mission to Mars, for example.
Okay, I'm all ears. Tell me more about how this equation helps us get to Mars.
Well, imagine you're designing a spacecraft's trajectory to Mars. You need to know the gravitational field strength, G, at various points along its path to calculate the necessary fuel and make course corrections. But measuring G directly from a distance can be tricky.
So how do we figure out G if we can't measure it directly? Do we just guess?
That's where PERC comes in. It turns out that measuring gravitational potential remotely is often easier. And thanks to our handy equation, we can use that potential data to calculate g at different points along the spacecraft's trajectory.
So we're basically using this stored energy concept to figure out the actual force the spacecraft will experience. That's pretty clever.
It is, and it highlights how this equation isn't just a theoretical curiosity. It's a practical tool that helps us explore the cosmos.
This is mind-blowing.
Yeah.
And to think it all stems from this one elegant equation. G, d dot r. It's like a key that unlocks a deeper understanding of gravity.
Exactly. And that's just the beginning. This relationship between G and A helps us understand not only spacecraft trajectories, but also the behavior of some of the most extreme objects in the universe, like black holes.
Black holes. Now you're really speaking my language. Let's dive into that. Tell me more about how this all relates to those cosmic beasts.
All right, let's talk black holes. These objects have such an immense gravitational pull that nothing, not even light, can escape them.
Yeah, that whole escape velocity exceeding the speed of light thing,
Yeah.
pretty wild.
Exactly. Now picture the event horizon. That boundary around a black hole beyond which there's no return. At the event horizon, the gravitational potential that we've been talking about becomes infinitely negative.
Infinitely negative. That sounds pretty intense.
It is, and this infinite potential means that the gravitational field strength, G, at the event horizon is also infinitely strong.
So anything that crosses that line is basically facing an irresistible force. No wonder nothing escapes.
That's the current understanding, and it's a powerful illustration of how this seemingly simple relationship between G and Ek, captured in our equation, can actually reveal the extreme nature of these fascinating objects.
You know, earlier you mentioned how engineers use this equation for things like planning missions to Mars, but it's amazing to think that the same principle applies to something as mind-boggling as a black hole.
It really highlights the universality of physics. These laws, these equations, they govern everything from the smallest particles to the largest structures in the universe.
It's making me think about that aha moment you mentioned at the beginning. I feel like I'm starting to grasp it now. It's not just about the equation itself, but about the deeper connection it reveals between potential energy and the force of gravity.
That's exactly it. This equation allows us to see how one flows from the other, how the rate of change in potential energy dictates the force we experience.
And this applies everywhere. From an apple falling to Earth, to a spacecraft navigating to Mars,
Yeah.
to a black hole warping space-time.
Precisely. It's a fundamental principle woven into the fabric of the cosmos.
Okay, this might be a bit of a tangent, but this conversation is making me wonder, if potential energy is like stored energy, is there a way to actually tap into that gravitational potential? Could we extract energy from a gravitational field, like we extract energy from fossil fuels?
That's a fascinating question, and it's one that scientists are actively exploring. The idea of harnessing the power of gravity is both intriguing and potentially revolutionary.
It almost sounds like science fiction.
It does, doesn't it? But the idea is rooted in real science. After all, we see the effects of gravity all around us. It's what keeps our feet on the ground, what drives the tides, what governs the motion of planets and stars.
So you're saying that this force that shapes the universe could also potentially be a source of energy for us?
That's the hope. Of course, there are many challenges to overcome. Extracting energy from a gravitational field in a practical and efficient way is a complex problem.
But if we could crack the code, the possibilities would be immense, right?
Absolutely. Imagine a world powered by the very force that holds the universe together. That's the kind of breakthrough that could redefine our future.
That's truly a thought-provoking idea. And it all circles back to that same equation, that connection between gravitational field strength and potential. It's a reminder that even the most seemingly abstract concepts can have profound implications for our understanding of the universe and our place within it.
It's a testament to the power of physics to reveal the hidden connections in the world around us and to inspire us to push the boundaries of what's possible.
So if any of our listeners out there end up cracking the code on gravitational energy, they know who to call first. In the meantime, I think this deep dive has given us all a lot to ponder. So what does all this mean for you, our listener? Why should you care about this connection between G and Hera home?
Well, for one, it helps you see the universe a little differently. Instead of just separate forces and energies, you begin to understand how they're related, how one flows from the other.
It's like glimpsing the underlying code of the universe.
Exactly. And remember, this isn't just theoretical. Engineers designing satellites, physicists studying galaxies. They all use these principles in their work. It's a fundamental part of how we understand and interact with the cosmos.
Our source even has this cool interactive simulation where you can change the mass of an object and see how the field strength and potential change around it. I was playing around with it earlier, and it really helps visualize these concepts.
Visualizations are so powerful, aren't they? They can make these abstract ideas click in a whole new way.
Yeah, I always find that seeing things in action makes them much easier to grasp. Okay, so before we wrap up, I have to ask, any final brain-exploding thoughts for our listeners to ponder? Something to keep them thinking even after this deep dive.
Here's a question for you to consider. If gravitational potential is all about stored energy, could we somehow manipulate that potential to create artificial gravity? Think about it. Generating gravity on a spaceship, or maybe even on other planets.
Whoa, now that's a thought. Artificial gravity. It's the stuff of science fiction.
It is. But who knows? Maybe someday, with a deeper understanding of gravity and its relationship to potential energy, it could become a reality.
That's definitely something to ponder. So to our listeners, if any of you figure out how to create artificial gravity, you know who to call first. In the meantime, be sure to check out the link to the source material in the show notes. The interactive simulation is definitely worth playing around with. It really helps bring these concepts to life. Until next time, keep those minds curious and keep exploring the wonders of the universe.